Can you hear me, class? Okay,
Yes, sir.
thank you, Lakshika. Right, Gaurav. Okay, thank you. Thank you, Mohit. So let me share my this thing again and desktop, and then we start, right? So let me share my desktop first, and then of course we can start. So here we are, and we would do two things today. One is ggplot, and the other is deploy if time permits. So let's begin. First, of course, we start with. And you see this beautiful graph, so we'll try and make this graph today. But before that, let's get started with the data frames, right? So let me just start with that first, and then we move on and we talk more about this as we move along. All right, so here we are. So let's say we generate a vector first, and this time we're generating a vector using the random command. So we say vector1 equals to run if, and we're generating 20 numbers from 20 to 30. So the format is the number of numbers that you want to generate is given first, then you give 20, which is to start the limit. So you are generating numbers from 20 to 30, and you're generating 20 such numbers, right? So this is another way of generating a vector. So vector1 equals to, and you are saying round because you want round numbers here, right? You don't want numbers with decimals so that it becomes complicated. So we say round. So whatever numbers that are generated here will be rounded to the nearest whole number, right? So vector1 is equal to round runf 20, 20, 30, which means you are generating 20 numbers from 20 to 30, right? So you run this, and let me just clear out everything first. It is always a good practice to clear out whatever you've run before, because sometimes there could be variables that can collide, right? So here you are, you start with generating a vector, you say run this, and then you print your vector, and this is a random generation. So if you run it a second time, it will give you a different set of numbers. So let me run it again so that we get the final vector that we're going to work with. So here you are, and you can see these numbers are different from the previous numbers. So this is a random generator. You can generate random numbers 15, 20 to 30, whatever limits you define here, and the number of numbers you want to generate to define in the first argument to the runf command, right? Then we check the class and dimension of vector. Dimension of vector is, anyone? What is the dimension of a vector?
So
Very good.
Dimensionless.
Karnika, Lakshika. Good. So we can check the class of vector1. So this will come as numeric because these are numbers. And then the dimension is basically here, it is null. Then we convert it into a matrix, and because we have 20 numbers, we'll convert it into a row and column of 4 into 5, right? Remember, the row number is written first and the column number is written second. This we done yesterday. So we say matrix 1 is equal to matrix. And in the matrix, the values that we're going to give are from the vector 1. And we define our n row equals to 4 and n col equals to 5. And because we're not defining how it is to be arranged, it will be arranged by column, right? So you say run again, and then you print your matrix. So this much we had done yesterday. So what we're trying to do now is to move from vector to matrix to data frames, which is the main data type that we'll be using in R, right? And today we'll do that, and we'll move forward and try and use deploy package to try and answer some questions on the human genome. So here you are. This is what you have. You can see this is arranged by columns, so 21, then 27, then 26, then 29. And you could have said by rows equals to true, so that it would have arranged by row, right? Then we move on and we again check this is class of matrix 1. So this will be matrix or array. This is what you get here. And if you check the dimensions of this, the dimensions would be, what will be the dimension of this matrix class? Anyone?
So none.
The dimension would be, I don't see any messages, 4 into 5. Okay, so which is fine. We've already defined here. So Bhavya says 4 into 5 and others also say 4 into 5. So this is fine, right? So here you are, you have 4 to 5. This one. Then we convert a matrix into a data frame. So first we create another vector where we give names of students. So who wants to be here in this name list in the data frame? Raise your hands. Anyone who wants his name here, his or her name here, raise your hands. So Vasvi, Bhavya, and Prita. All right. And Shubham. So if I have read this correct, first 4, VASVI, Vasvi, Bhavya, and I forgot the remaining names. Okay, Arpita is right now there. So Arpita has raised her hand. So let me say Arpita, Arpita. And then I say Manisha. All right, so we'll say Manisha. And I missed a message here. There was some long message. All right. So here you are. So what we're doing is we are now creating a vector called students, right? And in students vector, we are concatenating the name of 4 participants right now. Vasvi, Bhavya, Arpita, and Manisha, right? And then you say data equals to data.frames, and you add students to your matrix one that are already declared, right? So basically you are now filling up your data frame. In the data frame, you can have both characters as well as numeric data types together. That is the advantage of the data frame. In a normal vector, you can only have either the numeric data type or the character data type. You cannot have both. So the advantage of data frame is that you can have both your numeric as well as character data types within the same table. And now that, when you take a biological data, typically you will have both, you'll have character variables and you'll have numeric variables, right? So let's say you're looking at the gene, so you could have expression level of a gene, and then you could have whether you're looking at exon or whatever. So therefore you have all types of data. So therefore the normal data type that we use in biological data analysis is a data frame, right? You have categorical variable and you also have numerical variables, right? So therefore, data frame becomes the most common data type or data structure that we use in biotechnology, right? So here we are creating a data frame now. So we say data equals to data.frame students matrix one. So students is this vector here and matrix one is the matrix that we have. We are combining the two together. So you say run. Students not, okay, so we have not run students first, right? So we'll first run students. Here you are, and then you run this data frame students matrix one, right? So because it's not run students, so it says there is a problem. Now you see what is there in data. This is now a data frame. So if you see here, you have your students, Vasvi, Bhavya, Arpita, and Manisha, 4 students, and these are their marks that they've obtained, let's say, for example, right? So that is what you have. And here, if you see, you still have X1, X2, X3, X4. So we'd want to replace the header with students and names of subjects in which they got these marks, for example, right? So what we do is, and then of course you can check the class of data. So data is the data frame in which you've got the new data frame. You run it, and you have this class as data.frame, right? Everybody, you're following?
Yes, sir.
I have not put up the,
Yes,
I've
sir.
not put up the headphones. Okay. Okay, so most of you say yes, and that is fine. My headphones are on, so therefore I couldn't hear anything. So in case you're speaking, I didn't hear. Now, of course, I'm on the free on the speaker, so you can speak up also. So let's move on and we talk now more of it. So now what we'll do is we'll create another vector, headers, and in headers we concatenate the name of the student. So I moved the console on the top here. So you can do that by moving up here. So somebody wrote a question, how did you move the console here? So this 4 squares that you see in our studio, you can move your console on left, that will come to the bottom, or on right? So if I do it here, the console will come on the left, and the environment variable will move to the environment panel will move to the right? And because you have defined 4 into 5, right? You said n row equals to 4, n col equals to 5. So whenever you say the dimensions of a matrix are, what is the dimension of the matrix? You write the row number first and the column number later, right? So that is, so I incidentally happened to see that question. Questions move very fast. The message time is very low. All right. So coming back here, class, what we're doing now is let me just move it again to the original position so that you follow the way we do it. So here is your console, here is your environment variable, right? So we create another vector. We say headers equals to concatenate, and then we say student, genomics and proteomics, nanobiotechnology, microbiology, and biostatistics. These are the 5 subjects in which you are presumably getting these marks, right? All random, but just to make it a proper data frame. So you say run this, right? So now you have this headers vector, and now you say call names. So column names data is your data frame equals to headers. So what you're saying is that the column names are basically whatever is there in the headers is your column names. So you are now adding another header to the data frame. You say run this, and then now you run your final data frame here, which is in the object data. You run this here, and this is what you get. So this is your student name. This is the marks obtained in genomics, marks obtained in proteomics, marks obtained in nanobiotechnology, microbiology, and biostatistics. So these are subjects that I usually teach. So therefore, I picked up these subjects, right? So this is your data frame now. This data frame, if you see, this is basically your data frame now. Now, let's say you want to add the total marks obtained by each student in the 5 subjects, right? So this is an base R, you can do that. And today we'll also do one more data frame, which will be about the human genome. And there we'll do the analysis using Depler. Depler is a specialized library for, text, data wrangling, data, data formatting, and so on and so forth. So we'll go to that in a moment from now, just to show you how it is done in base R. So if you want to do the, let's say now you want to add a new column where you want to calculate the total marks obtained by the students, right? So total marks obtained by Vasi would be the row of the sum of the rows, right? So 21, 21, 24, 28, and 29. So what you say is data dollar total marks. So in base R, it is defined if you want to add a new column, the column name is given next to the data frame with a dollar sign. So data dollar total marks. So new column will be created that will be called total marks is equal to row sums. This is self-explanatory. You are summing up the values in the row, and how do you give which columns are you summing up? So again, you mentioned with the open bracket data, and then again with square brackets, because you're summing up the this one here. So you say data, square brackets, you say comma, and then you sum up the values in column 2, 3, 4, 5, and 6, right? You are not summing up column 1, which is the character vector. So you cannot in any way sum up. So 2, 3, 4, 5, and 6, right? And you can see there is a whole lot of brackets and everything that you need to give. So this is quite a problematic way of doing it, which is available in base R. So therefore, what people have developed is Depler. Depler is a really more intuitive and very easy way of doing the same thing in R, right? So therefore, you have an advanced level package that is called Depler that can do this easily for you. But let's see how this works out here. So what you're doing is basically adding up these values in column number 2, 3, 4, 5, and 6, right? And then you create a new column, which is called total marks. So when you run this now, you get a new column that is total marks, which is basically a sum of the individual marks obtained in the 6 columns. Everybody, you're around? You follow? Okay, okay. So this will require a bit of practice also, right? So I'm sure you would have done a bit of practice before you came today, but this will require a regular practice. And of course, we don't do it this way. This is in base R. I'll tell you how you do it when you move on to Depler, right? Then if you want to calculate the average marks, so these are marks obtained in 1, 2, 3, 4, 5, 5 subjects, right? So you can divide your, again, you create a new column, average marks. So how do you create a new column in base R? You say the name of the data frame, which is data, dollar, average underscore marks. So whatever name you want to give to the new column, that is what comes up here, is equal to, and then here it is easy. You have already made the total marks column, so you directly access that. Again, name of the data frame, and then name of the column that you want to access. So data dollar total marks here divided by 5, right? So this is relatively simpler than aggregating several columns together. So you do that here, and then again you run this, and you get a new column that is your average marks obtained by students in the 5 subjects that I mentioned here. So this is how you do it in base R. This is a data frame. What is a data frame? A data frame can have both, it is a tabular format again, right? It will have rows and columns. And these rows and columns can have both character, logical, or numeric values. So basically categorical or numeric values can be present in specific columns. So this is the advantage, and most of the data that you have in biology will be having several fields, some of which will be having numeric expression, some of which will be having a categorical, plus minus present absent kind of data, or, exon, intron, or intron 5, intron 3, exon 5, exon 3, so on and so forth. Those kind of data will be there. So therefore, data frame is what you commonly use in biotechnology, right? And in everything that you use. The most common data structure that is used for data analytics is data frame, right? So we stop here with data frames. And now let me take you through a small presentation, which is called to introduce you to deploy. And then we come back here and we talk more, right? So why is this not happening? Everything is a problem today. All right. So here you are. Let me just put myself somewhere and let me just load this here. Right? So let me be here. All right. So deploy, right? So as I told you yesterday, that R has a lot of supporting libraries which are not present in base package of R, but can be downloaded as and when required, right? So this is deploy is one such library that is required for data manipulation, data parsing, data remodeling, and so on and so forth, right? So deploy is a powerful R package to manipulate, clean, and summarize unstructured data. So this is what is known as data wrangling. How do you install deploy into your R Studio? So I have shown you yesterday 2 ways of doing it. If you see here, let me escape this. And, okay, let me minimize this and let me do this here. So one is you can go to packages here, and in packages you could go to install, and in install you could. This is getting slow. I don't know why. All right, so you go to your CRAN repository and you can write dplyr, right? And you can select deploy. And then you click on install, it will install deploy into your system, into your R Studio, right? The other way of doing it is through command line. So if you want to do it through command line, you can directly say, you can go to new file, right? Let me just show you here into a new file. And you can say install install.packages packages, and in round brackets within double quotes dplyr, right? And installation has to be done only once. Once you have installed one time, you don't have to install it again. Next time you can directly call it and invoke it into your program. So once installed, in my case, it is already installed, so I will not use this. Once it is installed, you have to call it into your program. So for that, what you use is the library function, library, and the name of the library or package that you want to pull in. So dplyr. So you're now invoking deploy into your program, right? Everybody you follow. So this is for any typical library that you want to use. Let's say you want to use ggplot2. The process is still the same. You'll say install.packages, and then in double quotes ggplot2, and then library deploy. So once the package is installed, you don't have to install it again and again. Unless there is an update, you can update that. To invoke your package into the library, you have to write this command, library, and then in round brackets, the library name. Everybody you follow? All
Yes,
right.
sir.
Okay, good. So then we come back to deploy now, right? So let me close this here. Yeah, I don't want to save this. So we come to deploy. All right. And let me just show you the PPT for a moment, and then we come back here. Right, and here you are. Right. So this is how you install deploy, right? You can say install deploy, and then you can use library deploy to invoke deploy command. Then you could go to select columns, right? And here in this case, you can deploy has what is known as verbs. Am I audible, class? Everyone?
Yes, sir.
Okay,
Yes,
okay.
sir.
Because I pressed Control L, I thought I might have left, right? So what deploy has is what is known as deploy verbs, right? So deploy verbs, you have several types of verbs. For example, if you want to select a specific column from your data frame, you can use this select command, right? Then if you want to, again, filter by rows by a certain value, you can use filter. You can use arrange to sort in ascending order or descending order. You could use mutate. So like we were creating new columns for calculating average marks and total marks. Here in this case, you can use the verb mutate, which will create a new column. Then you could group by a certain criteria. So certain data, you can create a sub data set of the data set that you have by certain criteria using group by. And then you could summarize your data. So we'll have a look at how this is used in analyzing the human genome data, right? So let's get back to actual problem, and you should be able to follow better. And then, of course, I've told you how do you install Depler. The verbs select, filter, arrange, mutate, and summarize. There are other functions also, but these are your major functions that you can use. And then we'll come to ggplot2 in a later time if we have time, right? So let's get back here, and let's get back to now Depler, right? So here you are, and I'll keep myself here, and let me keep it to a blank here. So this is fine, right? All right, so here you are. Now let's get to Depler. So first, of course, is remember yesterday I told you you can set your working directory. The advantage of setting a working directory is that if you want to access a file in your working directory now, you don't have to give the file path, right? So first we'll set up the working directory. In this case, I say set wd, and then in round brackets, in double quotes, I give the path of my folder where my file is, right? So I'm in, this file is in F and R human genome folder. So I say F colon slash, this is a backward slash, and then R underscore human genome, whatever folder name you want, right? So if you, all right, so this is what you have. Then you can say get working directory. So just to confirm that you are in that current working directory, let me clear out everything from previous runs. And here you are. So you say first run this, and then you say get WD, you can run this, and you get you are now in FR human genome, right? Now, because the first time when I was doing this program, I had to install the package. So again, install.packages, and in double quotes, Depler, right? And because my file is an Excel file, I would also need a second package, that is read Excel. So that is also installed here. So we say install.packages and read Excel. So these are already installed, so I'm not installing it again. Then if you move on, now we want to load the libraries into this current program, right? So because you want to use them, you want to pick them up and load into the program. So for that, the format I've already told you, you say library, and then in round brackets, the library name. You don't require to double quotes here, right? So let me just run this first. So library read Excel is already uploaded, and then library deprel. So the way you can run this is either you can select the entire thing and run, or you could keep your cursor here at the end of the line or at the start of the line, and you say run, and you'll have library depreler also invoked into your program. So now you can directly access the commands and functions in library read Excel and library deploy. So what we do is we read the data first. So our data is an Excel file. So therefore we've used this read Excel library because that allows you to open a Excel sheet into your R. So we say HG, which is the object name into which we are reading the data that is present in this file here. So we say HG equals to read underscore Excel, right? So this is the command of the read Excel library that allows you to read an Excel file. And then in as an argument to read underscore Excel, you give the file name that you want to read. So this is how you do it. HG is equal to read underscore Excel human genome dot XLSX, right? So this is the Excel file. So when you run this now, the library has been read. So now you want to see the file has been read. Now you want to see the file. So the command to see the file is view HG with a capital V. Remember, right? So this is case sensitive. If you write small v, it will not show up. So when you say view HG, your library will be loaded in the next tab. Your file will be loaded in the next tab. So what is our file? This is our file. This is basically a file representing the human genome. Let me just pull down further. So here you are, you have this first column is chromosomes 1, 2, 3, 4 until XY, and then mitochondria is also included, right? Then the second column is the size of the chromosome in base pairs, right? Then the third column is the number of protein coding genes, the number of pseudogenes, the total number of long non-coding RNAs, total small non-coding RNAs, miRNA, and you have ribosomal RNA. How many of them are there, right? So this is 8 total columns and 25 entries, right? So this is your 25 entries, starting from 1 to 25, and this is your 8 columns. If you see here on top, 1, 2, 3, 4, 5, 6, 7, and 8, right? So this is our data frame consisting of this is your categorical variable. This is both, you have my mtDNA, X and Y, and 1, 2, 3, 4. And these are your numeric variables here. Everybody clear with this?
Yes, sir.
Okay.
Yes, sir.
Okay. So now this is the file that we got to work on, and there are some questions that we're going to answer now. So here you are. Again, you go back to deployed. The first question is, which chromosome has the maximum size? And we know by our experience that human genome was, when it was being numbered, the first chromosome was the largest, and among the autosomes, 22nd was the smallest. So that is how it has been numbered 1 to 22. But let's say that is not the case and you don't know. So how do you pull out the chromosome that has the maximum size? And somebody answered 1, which is correct, right? So because that has been numbered in that way. So to answer this, we're going to use Diplet functions, select, arrange, and slice, right? So these are the 3 functions we're going to use for Diplet. And one important thing that that I've not told you till now is this pipe function. So pipe function is represented as percent greater than percent. This indicates that to the data that you have now got, you're going to perform additional operations, right? So that is, so here and here, so this basically means you're going to perform additional operations on the data that you've obtained in the previous command here. So here, for example, what we do is first we read the original data into a buffer. So I say hg1 equals to hg. And then I say percent greater than percent or pipe, which means to hg1, I'm going to perform further operations, right? Then in hg1, I select chromosome and base pairs because I'm just looking for chromosome with the largest size. So I don't want additional data, right? So I don't want to tax my memory with reading the entire data frame. So I just do a subsetting of my data. And I'm only picking up 2 columns, chromosome and base pairs, right? So for that, you're doing the diplet verb that he uses, select. I'm selecting 2 columns, chromosome and base pairs, because these are the 2 that I need to answer my question. And then I say pipe again, percent greater than percent, because to this now I'm going to perform further operation. So what I do now is I arrange in descending order, and based on which column? Based on the base pairs, right? So in descending order, so that the highest comes on the top and the lowest comes at the bottom, right? And then again, I say pipe again, because I'm going to perform more operation here. Now that I've arranged it in the descending order, the chromosome with the biggest size would be on the top, right? So because I'm arranging on the basis of base pairs. If you look at our data here, okay, this is not the one. This one here, right? So I'm looking at 2 columns now, chromosome and base pairs, and I've arranged them in descending order so that the chromosome with the largest base pairs is at the top, right? And then what I do is I pull out the first value from here. So I say slice 1, right? So of hg1, in which I've selected 2 columns and rearrange them in descending order based on base pairs. I'm now pulling out only the first row of that and print, right? So now I say view hg1. So when I say view hg1, so let me just run everything complete here, right? So here you are, you say run. Now you see in hg1, you have the value of chromosome 1, and this is the chromosome 1 has the highest size, right? And you all already know that. Everybody here, class? You following?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. I need a louder and more emphatic yes, right? Okay. So this is what you have. So, and boys don't respond, right? Only the females are responding. All right. So here you are. One more time. What we are doing is first we convert our master data into a new object, which we are going to process. So hg1 equals to hg. And then because we're going to process it further, we use a pipe here. So pipe is to basically attach the input of the output of the previous command to the next command, right? And this is commonly if you do command line Linux, you would know that you can basically use a grep command to capture something and then pipe it onto a next command, right? Using a pipe. But here in this case, this is the pipe. Pipe is percent greater than percent. Instead of that vertical bar, in this case, the pipe is percent greater than percent, right? So we transfer our data into a temporary object here, and then we do our operations. First, we select for only 2 columns because we don't want others, because we only want to look at which chromosome has the largest size. So we are selecting chromosome name and the base pairs. And if you see, base pairs is in quotes because there is a gap in between. So ideally, when you make your header of the file, it is good not to have gaps. You can use an underscore if you want to, denote 2 different words, but it is always better not to have gaps. That may sometimes create problems. Then you pipe it further and you arrange in descending order, and then you pipe it further and you slice the first value here, and you now get it here, right? And if you want to write it to a file, you can write to a file. You say write.table and you say hg1 and file name, file equals to results.txt, append equals to false, and row.names equals to false. If you don't write row.names, then it will come as one, the typical one that you get here. So that will also come along with your thing. So therefore, you can write it this way, right? You can look at how you can use the write command. Write.table is basically to write tables. Now we come to question number 2. Everybody, you followed class? This is your deploy. First question is what we've done. Now we come to question number 2. So here, list of chromosomes with more than 500 pseudogenes and more than 1,000 protein coding genes. So you need to filter now to see which of these chromosomes have here. This is our original data. So we're looking at chromosomes that have more than 500 pseudogenes and more than 1,000 protein coding genes, right? So basically the command that you're going to use is now going to be filtered. So again, I say hg2 equals to hg. So I'm transferring the data from hg to hg2. I'm creating a new object, hg2, and this hg2 will be processed further. And then I use the filter verb of deploy, and I say directly pseudogenes greater than 500 and comma protein coding genes greater than 1,000. So this is our condition that we've given. So directly this value will come into hg2, and then we can say view hg2. So when you say view hg2 here, this is what you get. You say run, and here you are. So these are the chromosomes that have more than 1,000 protein coding genes and more than 500 pseudogenes. So you have filtered out your data, again, subsetted your data based on certain conditions that you're putting up here, right? So this is, again, how you can do it. Then you can write it onto table again. Then let's say you come to question number 3. Which 10 chromosomes have the highest protein coding gene density, right? So which means gene density means number of genes per megabase of genome, right? If you look at your data here, HG, there is no column that gives you gene density. So first you have to calculate your gene density, which means number of protein coding genes divided by base pairs in megabases. So this will be this value divided by 10 to the power 6. You follow class, everyone? What we're looking at is gene density now. Gene density is basically a way of normalizing your data because all chromosomes are not of the same size. So you need to normalize your data. If you're looking at, the larger chromosomes is obviously expected to have larger number of genes, but that may not essentially represent the actual condition here. So you want to normalize with respect to length. So therefore, what you're doing is you are dividing the protein coding genes by the length of the chromosome, and this length is in megabases, right? So let's see how you can do that. So first, of course, what you need to do is to create a new column. So to create a new column, if you remember from the PPT, the deploy verb is mutate. You are creating a new column, you're mutating your data set and creating a new column, right? So we are going to use mutate here. So again, first we transfer our file to a new object. This is hg3. And then we say mutate genes per megabase. So this is the column name that we're creating now. Instead of the dollar notation that we had seen earlier when you're doing the base R, here it is simple. We say mutate genes per megabase is equal to, and then you create your column name protein. So this is basically the protein coding genes divided by base pairs, which itself is divided by 10 to the power 6 because you're now calculating genes per megabase, right? So the size of the chromosome is given in absolute numbers, not in megabases. So that has to be divided by 10 to the power 6 to get megabases. And then that value will basically be used to divide number of protein coding genes that are present in this column here, right? So this is what you're doing. Let me just show you here again. Number of protein coding genes divided by the base pairs in megabase. So this divided by 10 power 6, 2058 divided by this value, which itself is divided by 10 power 6, right? So here you are, and then you can say view at G3. So this is what you get here. So this is, you run this and you get your HG3. So now what you've done is you've created a new column, genes per megabase, and you have certain values here, right? Our job is still not done because we want to now select for first 10 chromosomes with highest gene density, right? Sorry, I didn't see the message completely. To the left or right, something was there, right? So this is how you create a new column. So this new column will be added to the rightmost end of the table, right? So here you are. Again, let me take you through this again. The question was, which 10 chromosomes have the highest protein coding gene density? Genes per megabase, right? So for calculating genes per megabase, we do this division of number of base pairs divided by 100,000. And then for calculating the genes per megabase, you divide the protein coding genes by by the megabase size of the chromosome, right? And the way you do it is you create a new column, mutate, giving joint meeting. Sorry, I didn't get the message. It gets off very quickly. Can you speak up here? All right, so you say mutate and genes per megabase, protein coding genes, base pairs by 1,000, and then you can do this. Now our job is still not over because the question is which 10 chromosomes have the highest protein coding gene density. So again, you have to arrange this. So we transfer this to HG4, and then we say arrange, descending order again, genes per megabase. Now the column is already there, and then we process it further, and we select only the chromosome and genes per megabase from here, right? And then we slice it from 1 to 10, right? So we got the first 10 values we want to show. So we slice 1 is to 10, and then we say view HG4. This is our final result, right? So this is the second part where you arrange and select for only the two columns, and then you arrange it in the descending order, and then you pick up the first 10 values, slice 1 is to 10, right? So let me run this now. And when you run this now, here is what you get. So this is your genes per megabase, highest for the mitochondrial DNA. There is absolutely no repeat here. The genome size is small and the number of genes is around 32 or something. So this is the highest for mitochondrial DNA. Then the 19th chromosome amongst the human nuclear genome would have the highest gene density. And one surprisingly comes at the 8th number, right? So this is normalization with respect to length. With that, amongst the nuclear genome, chromosome 19 has the highest number of genes per megabase of the chromosome. You follow class, everyone?
Yes, sir.
Interesting.
Yes, sir.
Okay,
Yes, sir.
good. Now it is nice. Nice to listen to. Okay, okay, Gaurav and everybody says yes. Neha says yes. All right. So now what you're doing is, so there is another way of looking at it. First, we have answered this question. Now let's get to the final question. Question number 4, right? And you're saying calculate the mean of gene density for autosomes, for sex chromosomes, and mitochondrial genome, right? So what you have to do is now you have to group your chromosomes based on certain criteria. You say that this 1 to 22 is autosomes, X and Y are sex chromosomes, and the final one is the mitochondrial genome, right? So first, can you please share the scripts? See, sharing the script will not help. And these are all videos already present in my YouTube channel. You type it yourself. If you just load my script and do it, it will not work out. You watch the video and do it. If you want, I can share the script. That is not a problem. But then, you have to do it yourself. Remember, programming is doing it yourself. If you use somebody else's script, it will not work out for a very long time. Okay. So here you are. So these videos are available on YouTube. You can just go back and check and keep typing from watching there, right? That will help you, absorb and imbibe faster. All right, so question number 4, calculate the mean density of for autosomes, sex chromosomes, and mitochondrial genome. So this is what you have now, right? So what you need to do is, this is, okay. So this is my YouTube channel. Dr. Vipin's Biotech and Bioinformatics Classroom. It is called as Dr. Vipin's Biotech and Bioinformatics Classroom. Okay. I thought some of you had gone yesterday because I saw a lot of hits yesterday, right? All right. So let's go back here and come back here, right? All right, so here you are. So what you're doing now is question number 4, calculate the mean of gene density for autosomes, sex chromosomes, and mitochondrial genomes. So here you are, if you look at your data here, HG, this is your initial data. Let me close everything else, right? And this one also we can close. So here there is no way I can say that 1 to 10, 1 to chromosome 1 to 22 are your this thing, right? They are your autosomes, and then X and Y are sex chromosomes, and mitochondria is your mitochondrial genome. So what you want to do is first you have to have a category, a particular column which can help you identify which are your autosomes, which are your sex chromosomes, and which are your mitochondrial genome. So what we do is we first again transfer the HG3 to HG5. Remember, HG3 has your uh, uh, chromosome genes per megabase column, right? So this is what is important again, right? So because we are going to look at gene density, so we transfer HG3 to HG5. HG3 has your genes per megabase also, right? So if you see view HG3, it has an additional column that is genes per megabase. So this is your column here, right? So we are taking this data now, not the original data frame. We are taking this data frame, we are transferring it to the new object HG5, and then we are mutating it. We are adding a new column, and we are adding what is known as a column name type. And this type you define what each chromosome is. A for autosome, S for sex chromosomes, and M for mitochondrial DNA, right? And then we say view HG5. So let me run this part here. And you say run. And now you see you have this labeling here. These are your sex chromosomes represented by S. This is your mitochondrial genome, and the remaining ones are A autosomes. So you have added a new column here, which is your type, right? Everybody here, to add a column, what is the Doppler verb you use? Anyone? To create a new column, what is the Doppler verb that we use? Anyone? Bhavna, mutate, Bhavya, Kanika, and everybody gets it right. And yes, Lakshika and everybody. Good. So let's get back to the script again. So here you are. What we have done is first we have created an additional column to calculate genes per megabase. Now we create one more column so that we know we give a common identifier to chromosomes that are autosomes, 2 chromosomes that are sex chromosomes, and 2 chromosomes that is coming from mitochondria, right? Now what we'll do is we'll use what is known as group by. So now we transfer this to HG6 and we add a pipe because we are going to further process it. And we say group underscore by, and what are we grouping it with? By type. Because what do we want? We want gene density for autosomes, gene density for sex chromosomes, and gene density for mitochondrial genome. So we want to subset our data with respect to the type of chromosome that we're looking at. So therefore, what we do is we group the data depending on the type that it is. So if it is A, all data is clubbed together. If it is S, all data is clubbed together. If it is M, that data is clubbed together, right? And then you say summarize. And in summarize arguments, you say gene density is equal to mean of genes per megabase, right? So all autosomes, you'll get one value. For all sex chromosomes, you'll get one value. All sex chromosome means X and Y. And for mitochondrial, you'll get one value again, right? So you say summarize gene density equals to mean of genes per megabase. So mean of all autosomes together, mean of all sex chromosomes together, mean of all mitochondrial, there is only one. So you get them. And then you say view HG6. So this is how you do it. You create this and you run this. Lakshika, let's say we had we had to mark 1 to 23rd row A and last two with S. Can this be done in a single command, or do we need to write? You're doing it in a single command, and you can, yes, you can do that. You can define your, you can see how you can create a vector where you say A coming 23 times, right? So there is a rep command that for that, Lakshika. So just go back and refer to the rep command. So if you want the same value to be repeated X number of times, you can use the rep to say that, right? So rep is another, so because for lack of time, I'm not doing that. But you can, if it is the same value to come 100 times, obviously you will not type it 100 times. You can simply say rep and then define what value you want. It will be repeated as many times, right? So here you are. So this is what you do. But because that creates, sometimes people don't understand that. So I've created it the hard way of creating 23 different values here, right? So this is the rep command can be used to at least write A 23 times straight away, then write rep command and write S twice, and M of course is one, so you can, so this will shorten up quite a bit. Good, Lakshika, right? So go back and refer to the rep command, right? So coming back here, you finally have your data here and you run it. So let me run everything here from this point until here, and you run this. And here is what you get. So for autosomes, the mean density is 7.52 something something. For is very high, very small, and only genes are there. There is no repeats. And for sex chromosomes, the mean density, the genes per base pair is very low. If the chromosome column is not in order, that you have to do some basic ordering. So again, I mean, that is something that you need to, the file must have some basic properties to begin with, right? So you can sort it out in some way, right? Do that. Right? Not everything can be done programmatically. I mean, you can do it, but then that is unnecessarily going to complicate. You can, and you could also have one ONE, two WO, so on and so forth. So that would also work. So some basic dressing of the file has to be done before you start programming, right? And you should know the features of your file. That is also important, right? So that is how it goes. Okay, so good question there. So this is how you can use diplet. I've shown you 5 basic verbs in diplet. One was we showed you how much time is left. I don't have my watch here, right? So let me just skip this 12 minutes. So, okay, so we'll do a quick revision of ggplot because we have only 2 lectures for R, and then we probably will do a bit when we meet the next time towards the end of the month. Tomorrow I'm going to IIIM Jammu for a workshop again on genomics, and then of course I return on 25th. And then I think on 26th or 27th we have the next class that is for Galaxy. So we'll come back to Galaxy, right? So here you are. This is the diplet. We have discussed the basic commands here. Let me now take you to ggplot and very quickly show you a few things, and then we can extend until 8:10 at least, so that you still get to see some things. So we have discussed select, we have select filter, we have arranged, we have mutated, and we have summarized, and we've also done group by because you wanted to group your chromosomes on the basis of their nature of being autosome or mitochondrial or sex chromosome, right? Now we come to ggplot2. ggplot2 is for data visualization, and I've already told you it is basically a industry standard now for graphs and for publication quality graphs, right? Then we move on and we talk of GG. In ggplot stands for Grammar of Graphics, right? And this is basically created by Hedley Wickham. It is the de facto standard data visualization tool package in R now. The base R also provides you, base R will also provide you graphics, but these are now largely supplanted by ggplot2 because it gives you very high quality publication quality graphs. Offers a powerful graphics language for creating elegant publication quality plots, and ggplot2 allows to create graphs for both univariate and multivariate numerical and categorical data. So depending on whatever type of data you have, you can still create plots here. So what is the 5 key steps in plotting in ggplot2, right? So there are 5 key steps in plotting a graph in ggplot. First is the setup. So you read the data set, define your X and Y axis. That is normally what you do when you do a graph in Excel, or even if you're doing a graph paper. You'll take up the data set and define your X and Y axis. Then second, you define your labels. So you'll have a title of the graph, what is the graph depicting. Then you'll have also labels on what is represented on the X axis, what is represented on the Y axis. Then you will have the the theme, and the default is black and white. You could also have a colored theme. So this is, not so mandatory, but of course, the more color you add, the more distinctly you can show your features. So therefore, colorful graphs are always preferred. Then you have the facet, individual graph for each group in data with exactly same range, right? So you can basically group your data in some way and individually create your graphs. And I'll show you how this is done. You'll follow it better there. And then finally, you have the actual graph type, which is called as geom or geometry or the layer, right? So this is the actual plot type. You have a whole series of plot types that you can have in ggplot. So you have bar plot, box plot, violent plot, heat map, scatter plot. So depending on what is the nature of data that you have, you can decide which plot will best represent your data, right? So here we are. What is the data we are looking at? So we are looking at a data, which is basically the position, the number of cytosins in 3 contexts in Arabidopsis. So Arabidopsis, is a model organism for plant genomics. And we are looking at the epigenomics of Arabidopsis. This was the part of work that I'd done when I was in Paris at École Normale Supérieure, Institute of Biology, École Normale Supérieure. So basically, cytosins can undergo methylation in 3 contexts in plants. One, when they're next to a guanine, so CG. Then if they are into a CHG context or CHH context, where H is any nucleotide except guanine. So in these 3 contexts, the cytosine can undergo methylation. So the data that we have is coming from the latest assembly of Arabidopsis, that is trial 10. And we are looking at the table shows how many times a cytosine occurs in the 3 contexts in trial 10 assembly, right? So what we have is the data here, and the objective is to draw a bar plot to depict this data. So here is our data. Arabidopsis has 5 chromosomes. So you have this chromosome-wise distribution. You have chromosome 1, 2, 3, 4, 5. And then there are 3 contexts, the CG context, the CHG context, and the CHH context, right? And this is the count that you have in CG context in chromosome 1. And then this is count in millions again, a count divided by 10 to the power 6. So this is the data that we have. And we want to now represent this as a bar graph to show the appearance of methylatable cytosins in the 3 contexts, right? So here we go, and this is my website. Vipin's Classroom, and then of course my YouTube channel is also there. I've already given you. This is Dr. Vipin's Biotech and Bioinformatics Classroom. You can go here and directly look at the R playlist. So let's get started again, and we plot the graph here, right? So let me just take you to R now, right? So here you are, and here you are. And let me take you to the player is there, and I closed that particular this thing, right? So let me just open that file here. So I go to local disk F, and I go to R within final, right? So this is R within final, and let me go to advanced. And here I go to ggplot epigenetics. Let me just see what is this ggplot2. And this is what it is, right? All right, so here we are, right? So first, of course, you define which library you're going to use for the process. So we are going to use ggplot2. I've already installed the library, so I don't need to install it again. So I say library ggplot2, right? So this is to basically, and let me clear out the previous things so that there is no variable collision here. And let me just reduce the size of this. So let me clear this out also. It is always a good practice to clear out your buffer before you start a new program, right? So here you are. You first load your package into the program. So loading your ggplot2 library. Then we're also going to load the data.table library. So this is how you're going to read your data. So you use your this thing, right? And then in data.table, the way to read the file is by the command fread, right? So we declare a variable methylated underscore C and is equal to fread. And then we define, because we've not set up our working directory here, we'll have to give the complete path of the file, right? So we say in f r workshop.csv, header equal to true and separator equal to comma. This is the CSV file, right? So therefore, if you see here, this is the comma separated value file. So we'll define our comma and everything. So let me run this. So here you are, you have read your file. Then you can view your file here. You say view methylated underscore C. So that is going to show you the data in your file. This is our file here, right? So again, chromosome 1 to 5 in the CG context, how many cytosins? In the CG context, how many cytosins? And the CHH context, how many cytosins are there? This is our data. So data is already loaded now in the program. Now you move on and we in the wrong program now. Okay. So here you are. So you can look at the structure of your data if you want. So this is the data frame. You can look at the structure of your data. This will give you the details of what all columns are there and what is the specific type of data that is present. Then you could do a summary of your methylated C. So these are some things that you can try out. So this will, because for the categorical variable, it will not give you anything. But for the columns where there are values, numeric values, it will give you the first quartile, median, mean, third quartile, and maximum and minimum values, right? So this is something that we've done for the vector last time, if you remember yesterday. And you can also check whether there is an NA value in your data, because sometimes there would be an NA value, but in this case, there is not. So you can say is.NA methylated C. If there are values that are NA, it will show you a true value, otherwise it shows you false. So this is false for all the values that are there in your data. So there is no NA value here, right? Then you come back to plotting the graph. So first as the base setup. So you basically use the function ggplot for setting up the graph. So you say graph is equal to ggplot. Define your data frame, methylated C. Then you say aesthetics. So aesthetics is to set up your basic graph. So you say the x-axis equals to chromosome, the y-axis equals to count in millions, and then you say also the labels. So you say plus labs, and you say x equals to chromosome. So the x-axis will be labeled as chromosome, y-axis will be labeled as cytosine counts in millions. And you also get the title equal to cytosine distribution in H. Haliana. So you are setting up your base of the graph here. So you say graph is equal to ggplot, methylated C is the name of the data frame which you're going to plot. Then you define your aesthetics. You say what is your x-axis is going to be represented by which column, y-axis is going to be represented by which column, and then you define your labels, or which is in short form said as labs. So you can say plus and define your labs. X equals to chromosome, Y equals to cytosine count in millions. Title is also what you define. Again, it is going to be a string, whatever title you want to give. And then you can print your graph. So when you select this and run, you will be able to print your graph here. And let me move here now. So this is your base graph, right? And right now it doesn't have anything except the skeleton of the graph. Can you see that, class? Class, you see? Okay. So everybody says, yes, Aditya says yes, Karnika says yes, and everybody is all right. So what we've done is we first, Bhavya says yes. So we have a first skeleton of the graph that we want to make. What we've defined is the aesthetics, what is going to be in the X chromosome, what is going to be on the Y chromosome. Then we have defined our labels, what is going to be the representation on X-axis, what is going to be represented on the Y-axis, and the title, right? Then you say, now you define your columns. So you say graph 1 equals to graph. So the base graph plus, now you define what is the type of graph you want to make. So you're saying geom underscore call, which is a bar graph, right? So you say graph 1 equals to graph. So the base graph will be there plus geom call. And you don't give any arguments into geom call. And you say print graph 1. So when you run this now, what you get is the actual values in terms of on chromosome 1, how much of cytosine is methylatable, chromosome 2, how much is methylatable, chromosome 3, how much is there, and so on and so forth. But you don't see the context now, right? So this is incomplete data representation. We also have the context also with us, right? So let's add the context now. So what we'll do is, we say now you add depth to your data. Right now you have only the basic data. How many cytosines on chromosome 1 are methylatable? How many on 2, 3, 4, 5? So now what we want to add is, because we also have the context information with us. If you see, we have CG, how many are there, CHG, how many are there. So we would want to represent the entire data, not the partial data. So what we do is, we move on to, where have we moved on? All right, so here we are. So we say graph 2. So graph 2 is graph 1. So everything that was there in graph 1 is anyways there. Plus you say aesthetics. In aesthetics, you add an additional field, fill equal to context. So now your filling will be based on the context, right? So now if you see here, when you run this, you get your representation of what is the CG context, CG context, and CHH. And you see in all the 5 chromosomes, most of the cytosines are in CHH context, right? Everybody here, class? So in very simple steps, you can make a very representative
Yes, sir.
graph. Good. All right. So then, okay, very cool. Thank you, Lakshika. Then we move on and we make it a little more. So now, right now, what is happening is all 3 are in the same column. So we would want to move the 3 contexts in 3 different columns for chromosome 1, for chromosome 2, for chromosome 3. So how do you do that? So you say again, graph 3 equals to graph, the base graph, plus geom call. And in geom call, now you give argument position equals to dodge. So when you say position equals to dot and you say asset x will equals to context, which was earlier there, asset x will equal to context. Now what will happen is instead of just 1 column for all the 3 contexts, you'll have 3 columns for the 3 contexts for chromosome 1, for 2, for 3, for 4, for 5. So let's run this and let me show you how this works out. So you run this here and there you are, right? So here you are. So this is your now chromosome 1, CG context, CHG context, and CHH context. Likewise for chromosome 2, chromosome 3, chromosome 4, and chromosome 5, right? Then if you want all the CG context together for all chromosomes, the CG context for all chromosomes together for, yeah?
Sir, what is aesthetic means?
Huh?
Aesthetic, that graph one
Yeah.
is equals plus aesthetic.
Aesthetic is basically, so aesthetic is basically how do you embellish your graph? Right? How do you decorate your graph? Aesthetics, you understand, right? Something is very aesthetic means something is very beautiful. So aesthetic, if you remember in the first context, when we are defining, I told you, you define your X and Y axis, AES, X equals to chromosome, Y equals to count in millions, right? So this was the first part that we've done. And then we are saying, while X equal to chromosome, Y equal to count in millions, you also want to bring in the context also very clearly. So therefore, you give additional argument, aesthetics, fill equals to context. So based on the context, the color of the fill will change, right? And then also you
adding additional something to decorate or something.
You're in addition to the base, you now want a slightly more better representation, right? So aesthetics is basically the beauty of something in literal terms, right? So let's move on. So now what we say is we have done this. We say geom underscore call, which is to say we are making a bar graph, and then we say position equals to dot. So and we are giving the aesthetics will equal to context. So now you get in 3 contexts. Now let's say you want to put all CGs together, all CG together, and all CHS together. So that again can be done. You say graph 4 equals to graph 3 plus facet underscore grid. And in this, you give tilde and you say context, right? So let me show you how this works out. You'll follow it better. You run now, and you get this now. So all chromosomes, CG context is 1 graph. All chromosomes, CG context. So this is like your group by in your Doppler, right? You follow class? They're grouping by a certain criteria. In this case, the grouping is done by the criteria of the context of the methylation, right? So you do it, okay, so everybody says yes, right? And I see some new names. I'm not able to take the name. Before that, it goes off. So here you are. So this is what you have. Chromosome 1 together, chromosome 2 together, CG context together, CHG context together, CHH context together. So the same graph, what I'm trying to show you is how you can use various options and just one-liners that will change the look and feel of your graph, right? So this looks a lot more, appealing when you send your manuscript with such graphs, even if there are some bit of shortcomings, visually it is so appealing that people would want to accept it with minor modifications, right? Then of course you can change the color if you want, so you can define what colors you want. For example, here I define a color range. I define this is graph 5 equals to graph 4. So over and above graph 4. So can we add error bars? Yes, you can add error bars, right? You can add error bars. Of course, you have to add error bars. But this is absolute count, so there is no problem here. But of course, depending on how you go about what is the data, you can add error bars. These are absolute counts, so you don't really have an error range here, right? So you run it here, and let me show you. You are changing the colors of your bars here. Let's say you want to change the colors from the default. You can say, you can define what colors you want, and then you can have your colors, right? And this will take some time. It's got stuck, right? So it will come by, right? It may take some time. Let me refresh this here. I think that should work. Yeah, so here you are. So first one is brown, the second one is blue, the third one is red. And then if you want to theme black and white, base size 9, theme panel background, if you want to have a panel background with light blue color. So these are some of the options that you can try and figure out which way your graph looks. The graph is still the same, just that the colors and the background is changing. So these adjustments can be done here. And again, let me refresh it. So one final thing, how do you download? You have to export these graphs from here. So export, save as PDF or save as image, whichever JPEG you want, or as PDF, you can export from here, from this export option. And once you're done, you can remove them from the buffer by clicking on these. So you can say yes, and you'll lose this graph. So all graphs are laid over each other, right? So I mean, this is your earlier one. Then you say yes, and you can keep clicking. So you'll go back to your original graph. So every graph is being shown over and above the previous graph, right? So that is what it is. So this is your ggplot2. I guess we have covered quite a lot in 2 lectures that were given, and that is nice. Now the onus is on you. How much you practice is what is going to make you perfect, right? And remember, if you are in biotechnology or literally in any science that you are in, programming is something that you'll have to learn because data is huge. It cannot be, and you know the power of programming. Zuckerberg is a millionaire because of Facebook, right? And apparently Facebook may be very simple, but it is the biggest data as of now. Social media is the biggest data. All right, so you want this data set. So I'll give you the data set. Let me just show you here one more thing before we close, right? Let me just take you here. You can go to my website. It's called Vipin's eClassroom, VIPINSECLASS classroom, right? And if you click on this here, it will take you here. Is it down? No. So here you are. The first hit on Google is Vipin's eClassroom. And you can go back here. And this is my website. And here you can go to Vipin's brackets, right? So the file that I showed you is here, right? And the epigenetics file is also here. You can click on this and download, right? So here you are. So if you could click on this will take you to that file. You can copy from here or you can download the file. Likewise, the epigenetics file is also here. So you can click up here, and this will give you the R workshop CSV. You can download this also. This is a CSV. So I guess that takes care of everything for now. And we meet again on, I think, later half of the month, and we do Galaxy, right? So what you need to do before we go to Galaxy is create an account in usegalaxy.org. Everybody, create an account in usegalaxy.org. And if you're watching the videos, you can comment if you want to, and like the videos if you want to, right? So that is where we would want to close today. Let me just close this here. This is Vipin's classroom. Directly, the first step would be here, right? So let me close this. And right now I'm lost where I am because I don't see anything. Let me stop sharing. You're welcome, Asgar, and everyone else, right? Everyone else is welcome. Manisha and Drishya.
Thank you, sir.
Vasvi